Okay, welcome. I would like to give a quick lesson on something called the pigeonhole principle. Okay, what is the pigeonhole principle? First of all, pigeon is a bird, and once upon a time, maybe you would raise pigeons by constructing little homes for them and feeding them, and they would come back to your place where you feed them, and you can train them to send messages and things like that. I don't know anything about this. I'm half making this up, but you can create a sort of cubby holes for your pigeons in some sort of little holes, maybe like 8 inch squares on the side or something like that, just big enough for a little pigeon, 1 foot by 1 foot, whatever. And this is where the pigeons like to go and sit. And they do this amazing, incredible bird thing, which is that there might be a whole bunch of pigeons all just hanging out, somewhere else. And then suddenly they decide that they want to go back to their little pigeon holes. And suppose you have 9 holes and there are 9 pigeons. Well then, almost as if by magic, these 9 pigeons will all fly towards the pigeonholes, and though seemingly they're all going to crash into each other and there's going to be a big mess, in reality, due to some incredible bird skills, they are extremely sensitive to each other's actions, and in a blink of an eye, they manage to sort of self-regulate, and in fact, all 9 pigeons end up in the holes such that there's exactly 1 pigeon in each hole. So that's sort of an amazing and impressive thing. It's the same thing you can observe if you watch, hundreds or even thousands of birds all try to take positions on a tree or something like that. They don't seem to mess it up. They all seem to find a spot quite fluidly. So, that's all well and good, but what if you have 10 pigeons? Oh no. If you have 10 pigeons but only 9 holes, then despite this incredible ability of pigeons to find the free hole, if there are no free holes, and every one of the 10 pigeons does end up in a hole, and there are only 9 holes, well then the pigeonhole principle says that there must be a hole with 2 pigeons in it. And more generally, if we don't give pigeons credit for always spreading themselves out as much as they possibly can, we can say more generally, and this is the pigeonhole principle, that if you have 10 objects and you are trying to cram those 10 objects into 9 spots, then there must be at least 1 spot with at least 2 objects in it. So that's the pigeonhole principle. Here we go. I'll just state it now. In its most simple form, it says if n plus 1 objects are placed into n boxes, then at least 1 box has at least 2 objects in it. Okay, if n plus 1 objects are placed into n boxes, then at least 1 box has at least 2 objects in it. Okay, couple things to say about the pigeonhole principle. So it's very kind of powerful, and it seems to capture a style of reasoning that comes up a lot in discrete math contexts. And so we will see this again and again over the course. One thing maybe we should do is just prove it. Okay, in fact, I don't think Gossett does do the proof, and in fact a lot of people don't. It almost seems as if some people are putting it out as some kind of axiom or something like that. It seems so low level. But in fact, you can absolutely do a proof of this. And we can then talk about what we think about this proof, but okay, let's go. How is this proof going to go? Well, it's going to go by contradiction. So suppose not. Suppose, contrary to this statement, So I'll just say, first of all, I'll just say, suppose not. And so, well, okay. Skipping a couple of steps, let's just take as assumed the antecedent, which is that there are in fact n plus 1 objects and n boxes, and the n plus 1 objects do end up into the n boxes, then let's suppose that the consequent is false. Okay, and so I think it's helpful to translate this into some sort of kind of pseudocode quantifier logic, because there are a lot of quantifiers floating around here, and in addition to the quantifiers, there's these sort of at least sentences which can be a little bit confusing. So what are we really saying if we're supposing, for purposes of proof by contradiction, that this is false? Well, we're supposing it's not true that at least one box has at least two objects in it. While the claim that we're making, at least one box has at least two objects in it, is we're claiming that there is a box, so there exists some box with greater than or equal to two objects in it. That there is a box with greater than or equal to two objects in it is the conclusion of the pigeonhole principle, and by doing a proof by contradiction, we're supposing that that's false. Okay, just writing that down, possibly for some people, makes it a little bit clearer. Okay, maybe not. So if this is not true, then what does that mean? If it's not true that there is a box with greater than or equal to objects in it, then by doing some kind of De Morgan law on this, we see that it must be true that in fact for all boxes, we can say that box I, I'll call it, has less than two objects in it. Objects. Okay, I ran out of space. So if it's not the case that there is a box with greater than or equal to two objects, then in fact each box has less than two objects in it. You could have gone straight to here, I suppose. Okay, well, if every box has less than two objects, then here then what does that mean? It's maybe more convenient to talk about this in terms of integers. Well, if an object has less than, if a box has less than two objects in it, then it either has 0 or 1 objects in it. And so what we actually really know is that all boxes have less than or equal to 1 object in them. And if all boxes have less than or equal to 1 object in them, well, now what we can do is we can sum all the objects in all the boxes. So if we now take the sum from, well, say I equals 1 to n, because there are n boxes, of the number of objects in box I, number of objects in box I, well, if every single box has less than or equal to 1 object in them, then if you add up all of the objects in all of these boxes, then it's going to be less than or equal to n. Because you're adding basically 0 or 1 n times. So you're going to get n objects total. But now we have a contradiction because there are in fact n plus 1 objects in total. And yet our method of distributing those objects to the boxes on the assumption that the consequent was not satisfied has led to only n objects, and that's a contradiction. Okay, so that was very slow and tedious, but hopefully careful. There's still some sort of like informal reasoning going on here that you might wonder, okay, what's really going on here? All these boxes and objects and pigeons and whatever. It seems so informal. So maybe it's just worth saying that even though this is often phrased in terms of pigeons, this is almost kind of some sort of cute way of getting around the fact that really this is just some low-level fact about functions. And the most formal statement of the pigeonhole principle, although most people don't state it this way because it's not actually more helpful to state it this way, but for those of you who want to maybe understand a little bit deeper what's going on, This is really a statement about functions, and it says, suppose you have some function f, and suppose f is a function from A to B. So you have some set A and some set B, and okay, yeah. So then what it says is, if there's like n plus 1 pigeons in here and n pigeons in here, so suppose that the size of the domain, this is understood to be the A is the domain of the function, B is the codomain, and A, the size of the set A, is n plus 1, so you have these n plus 1 pigeons, and they're going to these n boxes, which is to say that the size of the codomain is n, then no matter what you do, you must be sending two objects from A to the same, or two elements from A to the same element in B. And so what the pigeonhole principle really says is that if all this is true, so if it's the case that a function from A to B has a size of the domain n plus 1 and size of the codomain n, then f is not 1-to-1, or f is not an injection. So you cannot find an injection from a set to a larger set. Have I done that correctly? So you cannot, from a larger set to a smaller set, you cannot do. I suppose I could just equally well phrase it as a surject. I don't know, this to me seems like the best way. Okay, good. That's the pigeonhole principle. Okay, there's more, and no reason to stop the video. Let's continue. Gossett goes straight from this to something he calls the generalized pigeonhole principle. Alright, so what is that? Well, this is the most simple, basic version of the pigeonhole principle, but then there are other ways in which we can extend it. Oh man. In fact, there's not just one way to extend it. So generalized pigeonhole principle maybe is a little bit misleading, because there are several different directions in which you might extend this. But one way is to just increase the number of objects beyond double the number of boxes. Okay, and so a good example of this, so I'll do an example first, is something that comes up a lot, and this is actually a problem from the textbook, and this is what I did in class as well. Imagine you have a job where you're paid a salary throughout the year, and you receive a paycheck every other week. That's in fact how I'm paid. So you get a bi-weekly paycheck. Every other Friday you get a paycheck. Well, there are basically exactly 52 weeks in a year, which means if you get paid bi-weekly, that you get 26 paychecks a year. And okay, most people are on a pretty tight budget, so they count on these paychecks to pay all of their bills. And bills include things like, electricity bill, gas bill, rent or mortgage, daycare, whatever, private school, things like that. Almost every single thing I just mentioned, in fact, for whatever reason, works on a monthly system. And so you might have a monthly rent check, a monthly electricity bill. And so if your bills are monthly, well then that means like something really exciting happens, and it's great, because you have then 12 bills that you have to pay in a given year, and yet you get 26 paychecks a year. Well then common sense says that there must be some month in which you get 3 paychecks. You might get a paycheck on the 1st of the month, a paycheck on the 15th, and a paycheck on the 29th. And that is a great month, because it means that though your bills are staying the same, suddenly you just get a huge bump in the amount of income you get, seemingly. It's sort of an extra little bonus to your budget. Okay, and that's the pigeonhole principle. What it sort of says is, if there are 12 months and 26 paychecks, and now thinking of the months as the pigeonholes and the 26 paychecks as the pigeons flying into the months, then there is at least 1 month in which, in fact there will be 2, in which there are at least 3 paychecks. So if all the paychecks, if all the 26 paychecks try to fly into the 12 month pigeonholes, then you will find 1 month with 3 paychecks in it. And where are we getting this 3? Well, we're sort of dividing, right? We're sort of mentally, we're saying, okay, well, what could you fit? Could the 26 paychecks fit into the 12 months with just 2 in each month? Well, no. They try to fit in with just 2, and then there's like some little bit left over. And so the general idea is you divide 26 by 12, and you get a little bit more than 2. And if you get a little bit more than 2, then you take the ceiling of that, and that's 3. And so somewhere in there, we have to have 3 paychecks in a month. Okay, so what is the statement then? The statement then, the generalized pigeonhole principle, and now I'll do it more abstractly, but it will still be just a statement about, pigeons and stuff, or objects. If n objects, are placed into k boxes, then at least one box has at least n divided by k ceiling objects in it. It's just the statement of the general principle that we just discovered over here with this example. Okay, so since we understand this quite well, maybe we just go straight to the proof. And the proof of this follows exactly along the lines of the proof of the regular pigeonhole principle. It's just a little bit more confusing. So, okay, so here we go. Let's see, how should we do this? Maybe I'll do the proof over here, and I'll use this left side for scratch work. So, okay. Once again, we do it by contradiction. So, suppose not. And way down here, we're going to hope for a contradiction. Well, what does it mean for the generalized pigeonhole principle to be false? Once again, I'll let there be n objects which have been placed into k boxes, and I will, without rewriting that, and I will suppose that the consequent of this sentence is false. So what does it mean? It means that it's not the case that there exists a box with greater than or equal to n over k ceiling objects in it. Suppose that there's not a box. The statement is that at least one box has at least that many objects. So there is a box with greater than or equal to that many objects, and we're supposing that that's false. Okay, writing it down like that maybe is helpful once again for some people. So now we see that by assuming that this is false for purposes of a proof by contradiction, then we distribute this negation through using some kind of De Morgan's common sense type thing. So all boxes, if it's not the case that there is a box with this many, with at least this many objects in it, that means that all boxes have less than n over k ceiling objects in them. Okay. All right. how do we use this fact now? Well, okay, I have found this quite confusing personally, the combination of the division and non-integers and the ceiling function and less thans and stuff. So I feel the need to take a step back and to give a kind of a definition of ceiling n over k, or perhaps just a definition of ceiling in general. Well, I guess we know what ceiling in general is. It's just sort of round up, right? Well, but maybe that's not formal enough of a definition for our purposes. So at least when it comes to the ceiling of a fraction, I think I can give a precise definition. So I would like to propose the following definition of the ceiling. So I'm going to go sort of down a step, lower level step here, and give a precise definition of the ceiling of a rational number, I suppose is what I'm doing. And okay, what is this sort of symbol saying for you to do? Well, it says divide n by k, and take the ceiling of that. Okay, well, this is a discrete math class, so there's no real, when you're dividing integers, what we're really talking about is seeing how many integers how many times k can go into n, and so that suggests that we should use the Euclidean division algorithm. So the Euclidean division algorithm says that every number, like n say, can be expressed as some number q of k's plus a remainder. This is the Euclidean division algorithm, where r, the remainder, is, and everything's positive here, so I ignore the absolute values, where r is at least 0, but strictly less than k. Okay, so the Euclidean division algorithm, which we proved earlier in the course, enables us to go straight to this. And now I can tell you exactly what n over k ceiling is. It is, well, it depends. There are sort of two cases. There is the case in which n divided by k is an integer, so that's the case where r is 0, and then there's the case where r is not 0. If r is 0, then in fact k just divides n, and then the ceiling of n over k is just n over k, also known as q. And that's if n divides k. If k divides n. Which is just another way of saying if k divides n, which is just another way of saying that the remainder is 0. And on the other hand, if k does not divide n, which is just another way of saying that r is not 0, then what is the meaning of the ceiling of n over k? Well, now you just basically add 1 to the quotient, the sort of integer quotient. You divide, you get that k goes into n q times plus some kind of remainder, and then you just go up to the next number, q plus 1. So, or we could write this as n over k plus 1. Okay, so having just established that now, I feel kind of much happier. I have this bad board situation. So now this enables me to not have to worry about this kind of in the middle of the proof. And it also suggests that any careful proof involving this symbol is going to have to deal with these two sort of cases, because they are kind of different. Alright, and so right away I'm going to go back to my proof by contradiction here and consider the two cases. Case 1 is that k does divide n. And if k does divide n, then based on my explanation I just gave over there, I know that the ceiling of n choose k is just n choose k. Oh, sorry, n divided by k, which is just q. Okay. Well, if that's the case that we're in, then I go now to the statement that I've assumed, the statement that's going to lead to a contradiction, and it says all boxes have less than that number of objects in them. So what I now know is, so all boxes have, in fact, just less than n over k objects in them. And this is just me substituting this symbol for this symbol because they're the same in this case. Well, if all boxes have that, then let me just take the union of all the objects in all those boxes. So take the union from I equals 1 to k, because I have k boxes, so I'm summing up all the boxes, and what, or rather, I'm summing up all the objects in all the boxes. So take all the objects in box I and union all those objects together, and what you get is a big set of objects. And what do I know about the size of that set? Well, if each box has less than n over k objects, and I now take the union of all k of those boxes, then I'm sort of just adding n over k. Well, I'll just write it. It's going to be less than n over k times k, because each box has less than n over k, and there are k boxes, so you're just sort of adding less than n over k, k times. And this is just n. And so what this now tells me is that, so we have n total objects, but that is a contradiction, because in fact we have, we have less than, so we have less than n total objects, because that's what this says, right? That is numbered. So we have less than n total objects, and that is a contradiction because we started with precisely n objects. Okay, so that was case 1. That was kind of the easy case. Let's now go to case 2, and in case 2, I now suppose that k does not divide n. This is the other option. And if k does not divide n, then based on this conversation, I can tell you that n over k ceiling is precisely, maybe here it's just better to write it as q plus 1. Keeping the meaning of q as the one from over here in the definition. So sort of just insert this definition of q. Okay, well, what does that mean? Once again, I can just go back to the very thing I have assumed that is supposed to lead to a contradiction, and to see what that means now in light of case 2. And what it means in light of case 2 is, I'll now say that so all boxes have, in fact, less than q plus 1 objects in them. Well, if each box has less than q plus 1 objects in it, well, then each box, in fact, has less than or equal to q objects in it. And this we can see is impossible. It's impossible for there to be these k objects, each box having just q objects in it at most, because now just union all the boxes, right? Once again, take the union from I equals 1 to k, there are k boxes, of all of the objects in box I, and this now yields all the objects. And if you take the size of this set, well, based on the previous line, if you have k boxes, and each box has q objects at most, then the total size of this has to be less than or equal to kq. Okay, so that means we have less than or equal to qk total objects, and that is a contradiction, because qk because R, well, but since R is not 0, that's the case that we're in, then QK is in fact strictly less than N. And we in fact have N total objects. And so we do in fact have N total objects, but this argument yielded that we have only QK objects, and QK is less than N, so that is a contradiction. Okay, this is a very slow, careful proof, so maybe you watch it on 1.5 times speed, but I think this explains the generalized pigeonhole principle pretty well and is a good proof of it. Okay, bye.